We flip a switch, the lights come on. It's that simple, right? We power our entire world with this incredible system we almost never think about. But what if I told you that whole system is way more fragile than we imagine? That it's constantly teetering on the very edge of a massive collapse? Well, today, we're going to dive into the wild physics and the strange paradoxes that make our power grid so incredibly vulnerable. And look, this isn't some sci-fi scenario. This actually happened. Back in August 2003, a single power line, sagging just a little too low, brushed up against a tree in Ohio. And that tiny event, it cascaded. Within hours, 50 million people, from the American Midwest all the way up into Canada, were just in the dark. Turns out, a software bug in an alarm system meant nobody even saw it coming until it was way, way too late. And that one event really gets to the heart of the mystery we're talking about, the absolutely astonishing fragility of our power grids. To really get our heads around this, we have to start with something I'm calling the blackout paradox. See, these huge outages aren't just about a piece of equipment failing. They happen because of the incredibly complex, interconnected way the grid is built, a way where the very systems designed for reliability can actually hide the seeds of their own spectacular failure. Okay, so at the core of any of these giant blackouts is something called a cascading failure. The easiest way to think about it is like a line of dominoes. When one power line or one generator shuts down, the electricity it was carrying has to go somewhere, right? It doesn't just vanish. It instantly reroutes onto all the other lines, following the basic laws of physics. But that puts more stress on those neighboring parts. And if they can't handle that extra load, they trip and go offline too, pushing an even bigger load onto the next set of lines. And you can see where this is going. The cascade just keeps growing. But here is where the story gets really, really interesting. It turns out a massive blackout isn't just about that first domino. The real key, the most important factor, is the state of the entire system before anything even goes wrong. And scientists found this incredible, surprising clue to that hidden state, and it was buried in decades of blackout data. Now, check out this pattern. When researchers graphed the size of blackouts versus how often they happened, they expected to see the really big ones being super, super rare. But that's not what they found. Instead, they saw this, a power law. Now, in plain English, that just means that gigantic, grid-spanning blackouts happen way, way more often than they should if failures were just random independent events. A pattern like this is a telltale signature. It means the system is operating in a very particular and very dangerous state. And that state has a name. It's called criticality. Think about it like this. Try to balance a ruler on the tip of your finger. It's a complex system, right? You're making all these tiny little adjustments. When it's in that state of criticality, it's perfectly balanced, but the tiniest nudge, just a small disturbance, can send the whole thing crashing down. Well, that power law data suggests our power grid spends a lot of its time in that exact same state, perched on a knife's edge. And this visual just shows it perfectly. When the grid is at a really low load, failures are just isolated blips. The chance of a big blackout is basically zero. At a super high load, any little failure is almost guaranteed to cause a total collapse. But right there in the middle, at what's called a critical load, the system hits that tipping point. And here, a small failure might just fizzle out, or it has a very real chance of cascading into something absolutely enormous. That's the danger zone. That's where you find the power law. So this leads to the million-dollar question, right? If this state is so dangerous, why would a system designed by some of the most brilliant engineers in the world for maximum reliability, why would it constantly be operating so close to that tipping point? Well, the answer is in this invisible tug-of-war between two powerful competing forces. So on one side, you've got this relentless economic pressure. We want to run the grid as efficiently as we can, right? That means pushing more and more power through the existing lines to meet demand and keep our bills down. But on the other side, you've got the engineers trying to ensure safety. So after a blackout happens, they study what went wrong and they add upgrades. They build in bigger safety margins. And this constant push and pull, a concept called self-organized criticality, naturally drives the system right up to that critical edge. And this is the punchline. This is the really counterintuitive part. Making the grid better at handling small, everyday problems doesn't necessarily make the whole system safer. It's almost exactly like preventing small forest fires. All you're really doing is letting all the dead wood and dry brush build up on the forest floor. The system feels safer, so you push it harder. You operate closer to the limit, until one day a single spark ignites this massive, catastrophic inferno that you just can't stop. But hold on, the story doesn't stop there. That classic model of a cascading failure, the dominoes, it assumes things happen in a fairly slow, step-by-step way. But more recent science is showing us some much scarier reality. The most dangerous cascades can happen literally at the speed of electricity itself.
You see, the old way of looking at it, the static view, saw a failure as this orderly sequence. A line fails, the system settles, another line fails, it settles again. But the new dynamic view shows that in the first few seconds after a fault, the grid is anything but stable. It's actually experiencing these wild, high-speed electrical oscillations, and components can fail because of these split-second transients long before the system ever gets a chance to find a new, stable state.
And this is what those crazy, ultra-fast failures can look like. During a huge European blackout in 2006, get this, 30 high-voltage lines tripped offline in just 19 seconds. This isn't a slow-motion domino effect anymore. It's a nearly instant shockwave that ripples through the entire system faster than any human operator could possibly react to. And guess what? Our new technologies are actually introducing new ways for this to happen. Let me give you an example. There's a new vulnerability called subcycle overvoltage, and it's pretty common with things like solar and wind power. So here's how it works. A small fault, maybe hundreds of miles away, causes a brief voltage dip. The inverters for the solar panels, to protect themselves, just stop providing power for a split second. But when that fault clears just milliseconds later, the grid voltage can surge back, and that surge is enough to trip the inverters completely offline. This exact thing happened in California in 2017, and 900 megawatts of solar power just vanished from the grid, almost instantly. Okay, so we understand the physics now, both the slow dominoes and the lightning-fast shockwaves. We get the economic pressures pushing the system to the brink. So that brings us to the final, really practical question. If we know what's causing these huge failures, why can't we just, engineer our way out of it? Well, as Professor Liang Du says right here, it really just boils down to a trade-off. It's about cost and risk. Sure, we could build a power grid that's pretty much immune to blackouts, but the cost would be astronomical, unthinkable. So instead, we operate based on a level of risk we've decided is acceptable. But the real question is, are we calculating that risk correctly? So most grids are built to what's called an N1 standard. All that means is the system has to be able to handle the loss of any single major component, one big generator, one big transmission line. But the problem is that huge 2003 Northeast blackout and another one in Iberia more recently, they were N2 events or even more complex. That's multiple failures all happening in a very short amount of time. We're building for one domino to fall, but the real world is showing us that sometimes 2 or 3 can fall at once. And this graph brings us right back to that prevention paradox, but it shows it in such stunning detail. This is a simulation showing what happens when you try to prevent small blackouts. The black line is the normal case, but look at the other lines. As you get better and better at stopping those small outages, that's the dip you see on the left, you end up driving the whole system closer to its absolute limits. And when a failure finally does get through your defenses, it's not small anymore. It becomes much, much larger. That's that dramatic spike on the right. We're literally trading everyday reliability for a much higher risk of total catastrophe. So here's the bottom line. Our power grid isn't some simple machine. It is a deeply complex, dynamic system that's constantly perched on the edge of criticality, always being pushed and pulled by the forces of economics and safety. And as we add new technologies like wind and solar and demand more from it than ever before, we have to ask a really tough question. Are all of our best efforts to make the grid more reliable actually making it more fragile? Or can this new, deeper understanding of how it fails finally help us build a grid that is truly, genuinely resilient?